Starting with the name of Allah, who is the most merciful and beneficent. My name is Muhammad Umar, along with my groupmate, Engineer Saqib Hussain and Engineer Ejaz Ahmed Somro. Today, we are going to present or FIP, a robust ultra-sensitive optical humidity sensor for environmental monitoring. This project is supervised by Dr. Muhammad Waqas Somro and co-supervised by Dr. Afaq Mansoor. We will be presenting this in the next slide: introduction, aims and objective, problem statement, motivation, literature review, methodology, material used for fabrication, results, and references. So in our introduction, optical humidity sensors have evolved through decades of research and development, constantly adapting to new demands and challenges. The continuous growth is supported by the emergence of a variety of optical fibers and functional materials, in addition to the adoption of different sensing mechanisms and optical techniques. The majority of optical humidity sensors reported to date highlighted trends in design and performance and discuss the challenges of different applications. So this is the background that how capacitive humidity sensor, resistive impedance, and thermal humidity sensor. Capacitive humidity sensor, poor relative accuracy, complex circuit because electronic circuit is required to change the capacitance in relative humidity. Temperature can affect the performance of the sensor. And resistive humidity sensor, sensitivity is low, not resistant to harsh condition. In impedance humidity sensor, the sensor with low response time may have degraded sensitivity. Highly sensitive sensor may have low response, as in case of metal, copper, sulfide, etc. Thermal humidity sensor, exposure to any gas with thermal properties different than nitrogen might affect the reading measurement. So this is the background of humidity sensors. Aims and objectives. The first objective is to design highly robust ultra-sensitive sensor based on optical conductivity of graphene using simple and cost-effective principle. The second aim is characterization. Sensors electrical and electrochemical characterization will be performed. The application like environmental monitoring will be demonstrated. The problem that we are going to reduce in the humidity sensors, that are the failures to detect the huge humidity of change, slow response and recovery time. For example, 30 seconds, 2 to 4 minutes, 60 to 9 seconds. These are all the time response and recovery time. We are going to reduce that to almost 3 seconds. Reproducibility, stability, cyclic performance, fabrication methodology, electron pattern, electrode pattern, construction mode, and cost incurred. Limit of detection is poor. Electromagnetic interference. In the previous sensors, resistive and impedance humidity sensor, the electromagnetic interferences are most. So in this circuit, there are no electric circuitry, so the electromagnetic interference will be neglected in this project. The motivation that why we choose optical humidity sensor are these motivation, that this sensor will be high response and recovery time, high sensitivity, ultra low detection limit, high stability and reproducibility. Temperature can vary, later affect to this optical humidity sensor. The literature that we studied about optical humidity sensor, the first one is high performance optical fiber humidity sensor based on lossy mode resonance using a nanostructure polyethylene and graphene oxide coating. The motivation and the oral summary of this paper was that this optical humidity sensor was designed using lossy mode resonance technique. Humidity sensor was achieved by combining polyethylene PEI with graphene oxide in a thin film. These two are mixed to enhance the sensitivity of that optical humidity sensor. Dicyanide was sputtered on the prepared thin film and fiber coat at a time. And the second paper that we studied in this literature and in this optical project, that was highly stable optical humidity sensor based on nano composite film. The motivation that we got from that paper and the oral summary of that paper was, in this research, glass substrate was washed with DI water to remove the impurities and dust. Quantum dots of cadmium telluride was spin coated on the glass substrate. Spin coated is one of the technique of preparing coating on the different substrates. After that substrate was kept for some time for drying, then cooled Ag particles were deposited on the cadmium chloride to increase the sensitivity and linearity. In last, sodium hydroxide solution was used to control the pH level to control the pH under 10. The methodology, the schematic diagram of our optical humidity sensor is that the first one is glass. The film that we make will be on transparent glass. The second is glass but washed with deionized water. First, we will wash that glass with deionized water to remove the dust particles and impurities. Then graphene coating will be done on that glass using spray coating technique. After that, that coating will be kept for some hours for drying purpose. After that, the design that we will be made on different softwares and print that design, the LED will be placed on the top of that design. The sample that we were prepared will be inside that design and the LDR will be placed below that design. And after that, when the principle of that humidity sensor, optical humidity sensor, that when we increase the humidity, the graphene particles react with that humidity, and the transparent properties of graphene will change, and the light will intensity will be increased gradually, and the light will be detected by the LDR. So this is the design that we made. This is the software design, and this is the design that we print on 3D printer. The design is square in shape, 1 by 1 inch. Net is made on the four sides of the design. There is also a place for LED and LDR on top and bottom respectively. There is also edges inside the design to hold the glass substrate. The glass substrate specification are rectangle in shape, 1.5 mm and 2 mm thickness glass was used. The length of that glass substrate was 23.4 mm and the width of that glass is 21.4 mm. So this is the last picture fixation design in 3D view. This is the solid work 3D view, and this is the 3D printed design of 3D view.
After that, there is a material of graphene material. We used a strong solvent, that is dimethyl formamide. After that, this is the complete methodology of our project. First of all, in step one, we are dispersing we are putting the graphene in the beaker, and step two, adding the beaker with the solvent DMF. I have told earlier. In step three, we are adding the solvent and DI water, because we tried different solvents for the dispersion of graphene. First of all, we used DI water to disperse the graphene, but unfortunately, the graphene cannot be dispersed. So after that, we used DMF. So in step four, you can see the dispersing of the graphene. We put solvent and graphene in a beaker, and then we put that beaker over a magnetic stirrer. So the after that, we took that solution in a coating spray machine. In step 5, we sprayed that dispersed graphene on the glass. In step 6, this is the final design and final sample of our sensor. After that, placing the component and glass substrate in a design. So this is the actual physical design of our project. From the top side, we put LED, and from the bottom side, we place the LDR. In between of LED and LDR, we put our optical humidity sensor. After that, there is a process of testing of sensor. First of all, we took a humidifier, and secondly, we took a chamber for the testing, and third is the complete setup in which we increase the humidity inside the chamber, where we placed commercial sensor for the comparison and our optical humidity sensor inside the chamber, and then gradually we started increasing the humidity. So after taking different regions and different samples, so here are the results of and sensor response of the sensor. So from the graph, it is clear that when we are gradually increasing the relative humidity, the resistivity of LDR is gradually decreasing. This graph represents that when we increase the relative humidity from 10% to 95%, then resistance decreased gradually. The sensor shows excellent sensitivity and linearity also. After that, this is the cyclic response of our sensor. The sensor's time response is calculated, that is almost 2.3 second, and the recovery time is calculated as 3.4 second. From the graph, it is clear that when we gradually start increasing the humidity, our response of our sensor showing that the resistance of the LDR is gradually decreasing, and when the 10 to 95% we increase the humidity, then we again start decreasing that humidity, and from 95% to 10%. So the increasing behavior of a resistance can be seen from the graph. So these are 5 cycles, but we have done almost more than 15 to 20 times. Sensor was tested for 5 cycles. The reproducibility of sensor was almost good. After that, there is the hysteresis. Actually, hysteresis is showing an error in the calculation, in the response. So first, you can see the graph, which is the positive response. It means when we gradually increase the humidity, that is the positive response, and then we start decreasing humidity, and that graph is almost comparable and parallel to that one, the first we took. So the gap between both of the graphs, forward and backward response, that is the minute error in the positive and negative response. From the graph, it can be seen that hysteresis is almost small. After that, I'm going to tell you that we have made different samples, but three compositions were selected for the composition of our sensor. First was we used the DMF 0.8 ml, and we used graphene 8 mg for the first sample, and then we made another sample that is composed of 1 milliliter of DMF solvent and 10 mg of graphene material, and we made a third sample that is composed of 1.5 milliliter of DMF solvent and 12 milligram of graphene material. So this is the graph that is showing the different samples which are discussed earlier. First one is the sample 2 graph that is in red color, and second is the blue that is showing the sample 3, and the blackish one is the sample 1. So when we took different readings and values of the sensor while testing, so sample 1 is looking quite linear and stable. So from comparing these three samples, we took sample 1 is the best to present here. So this is the our final the sample, that is sample 1, which is stable and linear. All, and after that, these uh, trials at initial stage, these were all the samples of our sensor which we made earlier. So after that, there is conclusion. In this work, we developed ultra-sensitive optical humidity sensor based on graphene. The graphene is coated on the glass substrate. The result indicates that the thickness of graphene layer depends on the sensitivity. The excellent response and recovery time was found in the sensing layer of 10 mg graphene. The designed humidity sensor has good repeatability and linearity. After that, we have a future recommendation that how we can enhance this made sensor. So if we use gold nanoparticles, that can be used to increase the sensitivity and overall performance of the sensor. After that, to make it highly efficient, use series of light detectors instead of one. After that, Replacing LED with invisible light is highly recommended to reduce the hysteresis of the sensor. After this, there is replacing Arduino UNO and ESP32 with MyRio could be a better option.